In this video, we're going to start with this research paper, 8-bit states in 2D floating gate memories using a gate injection mode for large-scale convolutional neural networks. And just being flat out honest, the paper is like pretty much as dense as the title, flat out. What caught my eye about it is that they have a unique method for CNNs. And then half of this paper is about neuromorphic computing, right? So they create a method for neuromorphic computing hardware, but then they simulate it utilizing CNNs, and then they are able to simulate and create this unique simulation method of this neuromorphic computing hardware method on CNNs. And so that's what's caught my eye, because if you've paid attention to my channel, I build CNNs a lot, right? Just because they're easy to build, they're computationally efficient, and I like them all around. they're easy to test with and to play around with, and then so in this instance, the major thing that they're doing is they're playing around with floating gate memories, or FGMs. On the hardware side, they're playing around with this, right? So they're switches, and they build it out. And we give the infrastructure, and then they also do this 8-bit precision programming process, which I really like, right? So with your typical CNN model, what it does is it converts an image to 2D data, right? So it'll be whatever the image is, it shrinks it to 2 dimensions. But this is saying that essentially when you're dealing with a small CNN, that's actually not enough data, not enough dimensions. And then so if you're taking a small CNN and then you quantize it to 8-bit precision, you're actually giving it more dimensions and more ability to process than the actual 2-dimensional layers. You're giving it 8 bits to process off of, which is better. And then so that's what this process does and implements in this particular instance overall. And then so again, they do it a lot. All of their paper is a lot on the hardware side. So right, they're building out the hardware, and then they give all of their diagrams are around building out the hardware and then testing the hardware. But But what I'm interested in is these last experiments, right? So hardware convolutions based on device arrays. And then so when they get into here, they simulate their method, and then they're saying that essentially they're getting almost perfect accuracy with their simulated method. And then so and then they give all of the here's all the steps, and then what they do, they 8-bit quantize the CNN layers, and then they create 9x2 arrays, and they give kind of all the logic and the math behind it, and then so it seems cool to me, right? So knowing me, the next thing I do is okay, let me take all of that, and then let me try to build it out, right? And then so very first thing is just so they have that 2D floating gate memory array, which is a really cool addition to CNNs overall, right? And then my first test is I input my resonance field over it, and just to see right what it looks like. I want to visualize this space, and then so this is I'm able to, and then so for that I want that for future studies. But then so focusing more on I can build out this space, and I can build out the geometry of this space, right? It was test 1. Test 2, let me build it out according to that research paper, right? And then I really like that 8-bit quantization method. And then so that's what I want to spend a lot of time on my first test is just quantizing the full model weights. So every layer of the CNN, right? And then so, and then I load and pre-process the MNIST data set. And then I build out the simulation layers, some of what, basically trying to create what they said in the paper, right? And then so, the first one, and then it's how you do it is so you need to you need to build out the class to quantize to simulate the quantization of the states, and then you need to find the first layers of you need to divide the layers of the CNN, and then so you need to do the math in order to do that, and then that's how you quantize them, right? And then you get the original weights, and then you quantize the weights based off of layers, and then you kind of do it and you set it back layer by layer, and then you simulate their that 9x2 array, And then it's all like, in this instance, it's all simulations, right? But then, so this is my first testing with it, and then my first tests are pretty bad. Like 27% accuracy on the training data set, and then 41% value accuracy is still low, and then 39% accuracy on the test. But like, what I do notice within this, that even with this bad test, is that my test accuracy is higher than my training accuracy, which is good, right? It's moving in a good direction. It's just like I'm doing something wrong here within this. And then what I realized, what I'm doing wrong within this is that I need to freeze those weights. So like, and it's a problem that I've run into with the Zyra models before. It's a simple element. So like, once I want to like train the CNN network, figure out where those weights are, freeze the weights, and then quantize. Like, it's like that same exact process that I've run through when I built out Zyra. So to me, it was like pretty straightforward within that as a next step, right? And then so I freeze the first 2 layers and then unfreeze the last 4 layers is what I end up doing within this. And then within that, and then I train it for 3 epochs, 98.7% on, like 98.6% on train, 98.7% on test. So there you go, right? But I do, so in this first instance, I do have problems still getting that CNN layer to like fully accurately output. So I've got a little bit more work to do within this instance. I read back to the paper, and then they utilize specifically like a few models within it. They utilize MobileNet and a few models that they point out specifically. And then I noticed, okay, so I need to also put in like this bipulse programming effect, and then utilize the MobileNet framework that they have within that. And then everything else is what I learned through the process of building this out. And then I just train it for 1 epoch within this instance. And then after 1 epoch, I get 97.95 on test, or on train, and then 98.841 on test. And then the CNN model is converging properly in this instance and updating its weights properly. And then so as we can see here, and then so beautiful test in this instance. And then so what I want to do then is like my very last test is like, so I want to be as close to the simulation as they provide in this research paper here. So that's what I try to do, right? And so I lay it all out. So it's the quantization and the bipulse programming simulation, data preprocessing, the MNIST data set, and then here's the model. That's the MobileNet model that they use specifically, and then they fine-tune the model, and then they compile it utilizing Atom and categorical cross-entropy loss, and then they quantize the convolutional layer. So I find the 2D convolutional layer, quantize it, unfreeze the last 4 layers, update the layer overall. So I just use all of their logic, right? And then that 9x2 array, like that 9x2 array is pretty cool to me, right? Because again, it's like most of the time you're dealing with like 3x3 arrays, and then so like they change it into a 9x2, and then so it's unique. And then so and then the full summary of what is all entailed here. Here's the full breakdown of the simulation that they give, and then within the paper. And then these results match the paper, right? They report these same like 98% or so on the paper. And then so here it is again, 98% on test, and then 97.9 on train. So like matching the paper and then what we see within the paper very explicitly. And then here it is, like it's the model's doing stuff, and it's updating and going through the way that it should. So successful testing overall. And then so this paper, very cool as to the framework that they lay out. It's again, if you're big into like CNN models and then like everything around that, this model it's very nice as to how it's benchmarking and performing, and then again it's a simulation of the hardware method and the FGM based hardware method that they lay out within this. So if you're interested in the hardware side as well, it's like, I mean, really useful research for that end as well. I don't have FGMs laying around, but so to me it was cool to play around with the simulation side of this, and then the simulation side is performing very nicely for their CNN models. And like I said, there is a part of this that I want to take for future models, which is this what I'm doing up here, and then combining resonance with this method, and it works Very nice overall. So I'm very happy and cool with this method. And if it's your first foray into neuromorphic computing, this is all a simulation at the end here of neuromorphic computing for you to play around with a CNN that is utilizing, yeah, it's a simulated method. So if you like this type of content, please like and subscribe. Thank you very much.